Hello everyone. In this project, I developed machine learning models to predict the credit default risk using the classification approach. The objective is to identify customers who are more likely to default on their loans. However, the goal of the project is not only to achieve the strong predictive performance, but also to ensure that the models follow the responsible AI principles, including the fairness, transparency, and the interpretability. To achieve this, I implemented a complete machine learning pipeline that includes the data preprocessing, the model training, the fairness analysis, and the explainability techniques such as the feature importance and the lemma explanation. So after loading the data, here is our data preprocessing. The data set contains the financial and the demographic information about the loans applicants. The target variable is a target, which indicates whether the customer defaulted on their credit. This is a binary classification problem where the model predicts a probability that a customer will default. Before training the model, I separate the features from target variables and remove the ID column since it doesn't provide the predictive value. The data set was split into three parts. The training set, about 70%, used to train the model. The validation set, about 50%, used for the model comparison and threshold tuning. The test set, about 50%, used for the final performance evaluation. Stratified space was used to preserve the class distribution, like here. So, uh, the credit default dataset are typically high imbalanced, meaning that the number of the non-default cases is much larger than the default case. To address this issue, I applied the SMOT, which is a semantic oversampling technique to generate the artificial sample of the mandatory class. The the SMOT helps the model better learn the pattern associated with the default case and improves the recall and F1 score. I also experiment with multiple sampling strategies such as the SMOT, the ADAS1, the random undersampling, the SMOT tomorrow. These were combined the different machine learning models, identify the best performing pipelines. So the model selection, like back to the model selection. I evaluated several models, including the logistic regression, the random forest, the histogradient boosting, the XG boost. Each model was trained with a pipeline that includes the preprocessing and the sampling techniques. The evaluation metrics used including the RCOU, the PRAOU, the accuracy, the precision, the record F1 score. Among all of the combinations, the XGBoost classifier with a small produce the best performance on the validation set. The XGBoost is a powerful gradient boosting algorithm and captures the complex nonlinear relationship and interactions between the features. So the threshold of optimization. Instead of using the default probability threshold of 0.5, I performed the threshold optimization to the better balance different performance metrics. For example, I search across multiple thresholds and evaluate the F1 score, the recall, the precision, and balance performance with a minimal recall constraint. This is important in credit risk prediction because missing default case can costly. Therefore, in some scenario, we may prioritize a higher record to ensure the risk broader and detected. So, responsible for the AI and fairness, the responsible AI is a key focus of this project. One potential concern in the credit risk models is bias against the demographic groups, such as the gender. To analyze the fairness, I perform a group-based evaluation using the code gender feature. For each gender group, I calculate the metrics such as the positive prediction rate, which relates the demographic parity, the true positive rate, the false positive rate, and this metric helps to determine whether the model treats different groups differently. And if there are large disparity between the groups, this may indicate potential bias in the model or the dataset. The fairness analysis is important because the credit models directly affect the financial opportunities, and the bias prediction could lead to unfair loan decisions. For the model interpret, so we're using the like right here the lemma and the shape explanation right here. So another important aspect of it is interpretability. Since the models like the attributes can be complex, it is important to provide explanation and helps the user understand how predictions are made. So I use several interpretive techniques. The global interpretability. The first analyze the feature importance from the attributes right here. Models feature the importance shows the variables contributes most to the model's prediction across the entire data set. So this helps us to understand which financial or demographic factors have the strongest impact on the credit default risk. The shape explanation, in addition to feature importance, I also use the shape, so which stands for the sharply addictive the explanations to the further improve. And it is based on the concept from the cooperative game theory and helps explanation how each feature contributes to prediction. It aligns the importance values to every feature for the specific prediction, showing whether the feature increase or decrease the predicted probability of default. Unlike the traditional feature importance, the shape provides both global and local explanation. At the global level, the shape summary plots show which the features have a greatest overall impact on the model's prediction. This helps identify the most influential variables affecting credit risk across the entire dataset. At the local level, the shape values explain the individual prediction by showing how each feature puts the prediction higher or lower. For example, the certain financial indicators may increase the predicted probability of default, where other factors may decrease it. This level of the transparency is especially important in financial decision making because the stakeholders such as the law officers, regulators, and the customers needed to understand when the particular prediction was made. By using the shape together with the line and feature importance, the model becomes more transparent, interpretable, and aligned with the responsible AI principle. So the line right here explain the individual predictions by approximating the model locally with simpler interpretable models. For specific loan applicant, the line can highlight which features contribute positively or negatively to the predicted default probability. This type of explanation is particularly used for the financial analyst, the regulator, the customer requesting explanations for the loan decision. The local explanation increases transparency and accountability is a machine learning system. For the ethic and consideration, there's several ethic consideration when developing the credit risk models. The first dataset may contain the historical bias. If the past lending decision were biased, the models may learn and reproduce those patterns. Second, the certain demographic variables may indirectly encode the sensitive information which could lead their unfair treatment. To mitigate this risk, it is important to monitor the fairness metrics to provide the interpretable explanation, regularly audit the model, and this step helps ensure the model aligns with the responsible AI principles. The production readiness, if the models were deployed in the production, the several additional steps will be necessary. The monitor model's performance over time, detecting the data drift, and continuous evaluating the fairness metrics, retrain the models with update data, and in addition, explanation tools should be integrated into the system so that the stakeholders can understand model decision. This improves the transparency and builds the trust in the AI-driven decision system. So in conclusion, this project demonstrates how the machine learning models can be developed with a strong focus on the responsible AI and builds a credit default prediction system using the XGBoost, address the class imbalance with the SMOT, and validates the performance with multiple evaluation metrics. So more importantly, I cooperate with the fairness analysis interpretability methods such as the feature importance and the LIME to make the models more transparent and accountable. By combining the predictive performance with ethic considerations, we can create machine learning systems that are both effective and responsible. Thank you.